All right, another really short clip from the Whitsitt v Professor Dave debate that shows just how many years Whitsitt is behind in this debate. So here's the clip.
Of course, also on a globe, the horizon should drop down and away from you as you increase altitude. What we see in reality is it rises with us, which is a major problem.
Why in fuck's name are you using a drone to try and measure the horizon, Whitsitt? Because I've got some really bad news for you, bro, if you actually use some precision equipment. And I hope that news doesn't bum you out too much. And that bad news is that the horizon does not rise with you as you gain altitude. And that's demonstrated pretty nicely here by a photo I took through one of my auto levels. So the crosshairs on the auto level are set at horizontal. And as you can see, the horizon is well below that. Not only that, we can use this photo combined with our knowledge of the globe to make a very good estimate for our observer height. And the way we do that is we use these two horizontal lines above and below the crosshairs, and these are called Stadia hairs. Now, what Stadia hairs are usually used for is to get an approximate distance away from the measuring rod. So in this case, the lower Stadia hair is at about 39 centimeters and the higher one is at about 85 centimeters. So the difference between the two is 46 centimeters. But what do we do with that number? Well, in the manual for every auto level, you will see it has a Stadia ratio. And every Stadia ratio I've ever seen is 100 to 1. So it seems to be the standard. And if we multiply that 46 centimeters by 100, we can work out that the rod itself is 46 meters away from the auto level. But why does that work? Well, let's have a little geometry lesson. So to understand the geometry, you need to first understand what a radian is. I imagine a decent proportion of the globers already know because they graduated high school level math. But flurfs on the whole tend to glaze over at this kind of stuff. So if we have a circle of any radius, which is the red line, and we lay out that radius along the circumference of the circle, then we make an angle at the center. And that angle at the center, when the arc length equals the radius, is the definition of 1 radian. And since the circumference of a circle is 2 pi r, then we can lay that radius around the circle 2 times pi times, which makes 1 radian approximately equal to 57.3 degrees. So let's jump into GeoGebra here for a minute. The blue shape is a sector of a circle, and the angle at the center is controlled by this slider. So it's currently at half a radian. And since the radius of that circle is 5, then the arc length is 2.5. The red shape is an isosceles triangle where the two long sides are the same length as the radius of the circle, and the small angle of the triangle is also half a radian. And if you do the trigonometry on that, you'll end up with a length for the opposite side of about 2.47. Now this red triangle is obviously meant to represent the view of the rod through the auto level. So the opposite side is that length that you measured between the Stadia lines. And then I've just calculated how much difference there is between the opposite side of the red triangle and the arc length of the blue sector, which right now is 1.05%. Now, what I want you to watch is as I make that angle smaller and smaller, you'll see that the red triangle and the blue sector start to become almost identical. And that error eventually becomes very, very close to 0. And it's this geometry that is the basis for what's called the small angle approximation, where we can equate a really small sector of a circle with an isosceles triangle. And you'll see now that the slider is set at 0.01 radians. That means the radius of that sector is 100 times longer than the arc length of that sector. Or in terms of the red triangle, the distance between the auto level and the rod is 100 times longer than the length measured on the rod. And that's what the Stadia ratio is. So the Stadia ratio means that this length here between these two Stadia lines is 0.01 radians, or 10 milliradians. And that's how we're going to measure the drop of the horizon through the auto level. So back to the auto level photo, we now know that the red arrow is 10 milliradians, and we're simply going to scale the yellow arrow against that, and we end up with 4.42 milliradians. Now when you do this, it's important to place the arrows as close as you can to the center of the image, because there's definitely some radial distortion going on, and we obviously want to minimize that. So 4.42 milliradians equals 0.253 degrees. But how do we get our observer height just from that angle? Well, there are a couple of ways to do it. Number one is on the left. You can use something like Metabunk, where you just keep increasing the viewer height until the refracted horizon dip gives you the result you need. Or you can use the dip correction formula from celestial navigation. So the dip in arc minutes equals 0.97 times the square root of the observer's height in feet. Or you can rearrange that in terms of its height, plug in all the numbers, and you get a height of 245 feet. And funnily enough, that's pretty spot on for my observer height. And if you're wondering why we got two different predictions, one of 238 feet from Metabunk and the other one for 245 feet for celestial navigation. It's because they use very slightly different values for refraction. So Metabunk infamously uses 7/6R, and 7 divided by 6 equals about 1.17, while the celestial navigation formula uses a radius multiplier of 1.20. So after dicking around for a few minutes with geometry, we can get back to the main point of the video, which is proving that Whitsitt is talking out of his ass when he says that the horizon rises to eye level. And that claim is coming from someone that also claims that celestial navigation has, quote unquote, been solved for a flat Earth. And that's obviously a lie, because if he's solved celestial navigation, then he's definitely seen the dip correction formula. And if he's seen the dip correction formula, then he wouldn't be saying stupid shit like the horizon rises to eye level. And again, that's pretty hilarious, because even the cult of Oakley has dropped that claim after they looked into celestial navigation. Now, so far we've only looked through an auto level to show that the horizon drops, but that's a pretty crude method, not really what they're designed for. The best tool for the job is, of course, a theodolite. So if you look closely at the photo, you'll see that the tripod is set up over a yellow cast iron plate, and underneath that plate is a surveying benchmark. And the height of the benchmark, according to the New South Wales government, is 39.559 metres. Add 1.7 metres for the height of the instrument, and our observer height is 41.2 metres, or 135 feet. So let's use the celestial navigation formula to work out what the prediction is for the angle down to the horizon, and we end up with a prediction of 11 minutes and 16 arc seconds. And have a look what I measured. Only about 10 arc seconds off, which is about 3/1000ths of a degree. So incredibly close to the globe prediction. But obviously, that's not the only measurement I've made. I've made stacks of measurements. And here are just two more. So I've given the observer location, the elevation, the globe prediction, as well as the measurement for both. And you can see that the measurement is quite close to the prediction in both of these cases. And just to drive the point home, here are those four observations plotted against the dip correction formula. So you can see just how tightly the globe model matches reality. Now, I've been asking the Flurfs for a while now for their geometry that explains this, but not surprisingly, no one has provided any. Anyway, to wrap things up, not only does the horizon not rise to eye level as you go up in elevation, but the angle between the horizon and eye level actually gets bigger as you go up in elevation. Hope that doesn't bum you out too much, bro.